Hey, what's up guys? This is Dr. Vivek Palipram bringing you the next lecturette in ECPE 127. In our previous lecturette, I discussed in great detail about the theory behind the Gaussian random variable, and we also discussed central limit theorem. We showed by example how the central limit theorem is so much prevalent in our day-to-day life. In this lecturette, we are going to put Gaussian random variables into action. Specifically, we are going to solve some instructional problems on the Gaussian random variable. Now, if you recall, the PDF, the probability density function of a Gaussian random variable x is given by 1 over root 2 pi sigma squared times e to the negative x minus mu whole squared over 2 sigma squared for x between negative infinity to infinity. That's your PDF for a Gaussian random variable. Now, the bad news is integration of a PDF for a Gaussian random variable is not straightforward using conventional methods. It happens to be one of the good news for us because the methods that we are going to use to find the probability that x, a Gaussian random variable x, belongs to a particular interval is going to boil down to a series of very simple steps. If we follow it perfectly, we'll get the probabilities easily. Now, the mathematicians have worked really very hard to tabulate the values for the standard normal Gaussian random variable CDF for different values of z. So what they have done is that they have tabulated phi of z, where phi of z gives you the probability that random variable capital Z, your standard normal random variable capital Z, is less than or equal to small z. So if we need to find probabilities pertaining to this Gaussian random variable, it makes sense for us to transform it to capital Z and then evaluate the probabilities for x in terms of probabilities for z. So let me give you those series of steps. Step number 1 is to subtract by mu on all sides. So when I subtract by mu from all sides, what I'm essentially doing is I'm transforming my Gaussian random variable to another random variable whose mean is equal to 0. So it is halfway there towards standardization. Next, I'm going to divide by sigma on all sides. Now carefully notice that x minus mu over sigma is actually your capital Z. If you recall theorem 14.14, any Gaussian random variable x with mean equal to mu and standard deviation equal to sigma can be written as a linear function of capital Z in this manner, sigma times z plus mu. And therefore, z is actually x minus mu over sigma. Now I'm going to replace x minus mu over sigma with z. So now I have this expression right here. Now I have expressed the probability that x belongs to an interval a to b in terms of probabilities that z belongs to this particular interval. Now I'm going to use the CDF property of z, of my standard normal random variable z, and obtain this probability as the difference between the cumulative distribution functions at the interval points. So phi of b minus mu over sigma is the value of the standard normal random variables CDF at the upper interval, and this one is the CDF value at the lower interval. I have just applied the simple principle that probability that x belongs to an interval is equal to f of x at b minus f of x at a. In this case, phi is the capital F for my standard normal random variable z. Next, I need to find the values of these two phi terms, and I can find that by referring to the standard normal random variable CDF. So we have a standard normal RVs CDF evaluated, or rather I should say pre-evaluated at different points. And I can refer to that table to find these values, and as a result I can also compute the probability that x belongs to the interval a to b. Now let me show you the CDF of a standard normal RV. It's uploaded on Canvas, so just go to Canvas and there you'll find this particular PDF, Gaussian CDF.pdf. if you notice here, this table shows you the values for the standard normal cumulative distribution function for different values of z. So I'm going to refer to this table to find out the values of phi, and then I can calculate the probabilities. Now here's a short snapshot or a small snapshot of that CDF table. This circled value that you see here, 0.8186, that's the value of the standard CDF at 0.91. So this gives you the probability that capital Z is less than or equal to 0.91. It is equal to 0.8186. Similarly, let's say this value right here, it gives you the probability that capital Z is less than or equal to 0.5, and so on and so forth. So let's solve problem number 1. The professor's TA tells him that students' marks on a test X follow a Gaussian distribution. 90 is the average and 6.5 is the standard deviation. And I need to find the probability that X is greater than 75.5 but less than or equal to 91. Now the equality sign really doesn't matter here because it's a continuous random variable. So the normal distribution, its parameters are the average is 90 and sigma value is 6.5. Now X is not a standard normal random variable, so I have to first use those steps to transform X to capital Z and then refer to my CDF table. From here onwards, we'll call it the phi table to find the probabilities. So step 1, subtract by mu on all sides. Now this mu is excess mu. So I'm going to subtract it. So I get 90x 91 minus 90, giving me probability, oh, I forgot x minus mu term here. So let me write it really quick, x minus mu. So x minus mu is less than or equal to 1, but it is greater than, this should be negative 14.15 or 14.5. Yeah, that's correct. Okay, next I'm going to divide by sigma on all sides. So I have probability negative 14.5 over 6.5 is less than x minus mu over sigma, which is less than or equal to 1 over 6.5. Let me quickly calculate these values using my calculator in my cell phone. So 14.5 divided by 6.5 gives me 2.23. So probability that x minus mu over sigma is greater than negative 2.23. And here I have 1 over 6.5. So that is 0.15. Step number 3 is to replace x minus mu over sigma with z. So now I have to find the probability that z is greater than negative 2.23 but less than 0.15. Step 4 is to use the standard CDF's property that the probability that your random variable belongs to an interval is equal to the CDF at the upper end of the interval minus the CDF at the lower end of the interval. So phi at 0.15 is the value of the CDF at the upper end of this interval minus the value of the CDF at the lower end of this interval. Now let me refer to this phi table now to get the values of phi at 0.15 and phi at negative 2.23. So let's find the value of phi at 0.5. So phi at 0.5. So I'll see how I can get phi at 0.5. So I'm going to look at this row right here. Okay, I'm not able to highlight it in using my eye pen here. So notice, oh, there you go. So notice the row of 0.1. So row of 0.1, and I'm going to go towards the right until I arrive at the column of 0.05. So this point right here, 0.55, or this value right here, the one above the highlighted one, 0.159, Okay, 0.5596 is the value of CDF at 0.15. So what I did was I first arrived at the row 0.1 and then I moved towards the right until I arrive at the column for 0.05, and the value that I see there is 0.5596. So that's the probability of z less than 0.15, which is 0.5596. Next, I need to find the value of the CDF at negative 2.23. Now let's find it out, the value of phi at negative 2.23. So first, I'll arrive at the column for negative 2, and then I'll move towards the right until 0.03. So that gives me, or rather, my apologies, I'll first look into the row of negative 2.2 because I want to find the value of the CDF at negative 2.23. So I'm going to look at the row of negative 2.2 and move towards the right until I arrive at the column of 0.03. So the probability there is 0.0099. So 0.0099. So 0.0099. So I can find this probability as 0.5596 minus 0.0099, giving me a value of 0.5497. So that's the probability that a given random mark is between 75.5 to 91. It's a little over 50%. So you can pause your video here and observe the steps that I have performed and how I referred to the CDF table. Now, pause this video here and try to solve this problem on your own. Once you have given it a fair shot, I'm going to solve part A and I'm going to solve part D for you. Okay, so let me solve part A first. Now in this case, x is a normal random variable with mean equal to 0 and standard deviation equal to 1. In fact, x is equivalent to z. So I can replace x with z because I don't need to perform any transformation here. So when I want to find the probability that x is greater than negative 1 but less than or equal to 1, I need to find the probability that z is greater than negative 1 but less than or equal to 1. In fact, when you see such a probability statement in terms of z, it's telling you the probability, or what is the probability that z is within one standard deviation. That's what it is telling you. So I do not have to transform this to anything because I don't have to perform those steps because it's already nicely in z format. So I am going to apply step 4 directly. So probability that z is greater than negative 1 but less than or equal to 1 is equal to phi at the upper end of the interval minus phi at the lower end of the interval. So I need to refer to my phi tables in order to find these values. I have to look at the phi table twice. First time to get phi of 1 and the second time to find out phi of negative 1. I can optimize this by using the property of standard normal distribution that phi of negative z is equal to 1 minus phi of z. So I can replace phi of negative 1 with 1 minus phi at 1, giving me 2 times phi at 1 minus 1. So I need to look at the CDF table just once, or the phi table just once. So let's find the value of the phi table at phi of 1. Okay, so the value of the CDF at phi of 1 is right here, 0.8413. So look into the row of 1 and you just go one step towards the right and you'll arrive at the column of 0.00, and there you will get the value of phi at 1, which is 0.8413. So that's the value, 0.8413. So this is 2 times 0.8413 minus 1, giving you 0.6826 as the probability answer. Now let me solve part D for you. We need to find the probability that y is greater than 3.5. Now y is actually not a normal distribution. I'm sorry, it is a normal distribution, but it is not a standard normal one. because its mean is 0, but the standard deviation is equal to 2. So I need to apply those steps. So step 1, let me call it step 1 properly, no shortcuts. Step 1, subtract by mu on all sides. So I get probability that y minus mu is greater than 3.5 minus 0. Then step 2, I divide by sigma, which is equal to 2. So I get y minus mu over sigma, which is greater than 3.5 over 2. Y minus mu over sigma is now a standard normal random variable. So I'll replace y minus mu over sigma with capital Z, and I need to find the probability that capital Z is greater than 1.75. Now this probability is also equal to 1 minus probability that Z is less than or equal to 1.75. Just recall that principle. Probability of A complement is equal to 1 minus probability of A. That's what I have applied here. So now I need to find probability that Z is less than or equal to 1.5. Probability that Z is less than or equal to 1.5 is just the value of CDF, of the normal CDF at 1.75. So I will consult my phi table to get the value of phi at 1.75. Value of phi at 1.75. So I arrive at the row 1.7 and I move towards right. So this is 1.70. I'm the right above. Oh gosh. Okay. Okay. All right. Let me not touch my pencil onto the iPad. So I'll go, this is 1.70, 1.71, 1.72, 1.73, 74, 75. The value 0.9599 that you see, that corresponds to the value of phi at 1.75, 0.9599. So I need to evaluate 1 minus 0.9599. So the value is 0.0401. That's the probability, 4% chance. And it is quite obvious, isn't it? Because if you would consider your normal distribution like this, your standard normal distribution, this is 0. Now you want to find the probability that Z is greater than 1.75. Your Z at 1.75 is right here. So you want to find the probability of this region right here, this teeny tiny region. Obviously, this is a small value, which is approximately equal to 4%. So there you go, guys. Those were the examples of solving probability problems with normal random variables. What I would recommend you to do is solve problem B and C on your own. Then on Friday's class, I'm going to give you some more interesting problems on Gaussian random variables. My apologies for the noise in the background. That's our nice pressure cooker making some nice rice for us. So I'm going to chow down on some rice. So adios.